Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The cosmic web that connects galaxies. When you look up at the night sky, the stars appear scattered across the darkness in what seems like a random pattern. Galaxies, those island universes containing billions of stars, seem to float in isolation, separated by vast gulfs of empty space. But zoom out far enough, pull back your perspective to encompass not just our galaxy or our local group of galaxies, but thousands, then millions, then billions of galaxies, and an extraordinary pattern emerges. The universe is not random at all. It's organized into a structure so vast and intricate that it resembles a three-dimensional spider's web stretching across the entire observable cosmos. This structure, called the cosmic web, represents the largest known organizational pattern in the universe. Picture it in your mind: long filaments of galaxies stretching across hundreds of millions of light years, connecting at massive nodes where galaxy clusters gather. Between these filaments lie enormous voids, regions of space so empty that they contain almost no galaxies at all. The filaments themselves are like highways of matter, channels along which gas flows and galaxies form, creating luminous threads that trace out the underlying architecture of space itself. The story of the cosmic web begins in the earliest moments after the Big Bang. In those first fractions of a second, the universe was nearly uniform, filled with hot plasma that was almost, but not quite, perfectly smooth. Tiny quantum fluctuations, variations in density that were only 1 part in 100,000, existed throughout this primordial material. These minuscule differences seemed insignificant, but they contained the seeds of everything that would come after. As the universe expanded and cooled, gravity began to amplify these tiny variations. Regions that were even slightly denser than average had slightly stronger gravity, which pulled in surrounding matter, making them denser still. This process fed on itself, with denser regions becoming denser over time, while less dense regions became emptier as their matter drained away toward the dense areas. But matter didn't just collapse into points, it collapsed along preferred directions, following the geometry dictated by the initial distribution of fluctuations. Imagine pouring cream into coffee and watching it swirl and fold into complex patterns before mixing completely. The early universe underwent something similar, but instead of mixing, the patterns froze into place, held there by gravity. Matter flowed along the paths of least resistance, streaming toward concentrations of mass, creating sheets and filaments rather than distributing itself uniformly. Dark matter played a crucial role in creating this web. This mysterious substance, which doesn't emit or absorb light but exerts gravitational force, makes up about 85% of all matter in the universe. Dark matter began clustering earlier than normal matter because it doesn't interact with light or other radiation. It formed a gravitational scaffolding, a framework of invisible mass and normal matter. The hydrogen and helium gas that would eventually form stars and galaxies fell into the gravitational wells created by this dark matter framework. The filaments of the cosmic web are not thin lines, but rather thick structures, typically about 20 to 30 million light years across, and stretching for hundreds of millions of light years in length. Along these filaments, galaxies form like beads on a string, though the string itself is made of dark matter with tendrils of gas threading through it. The gas in these filaments exists in a warm to hot state, typically between 100,000 and 10 million degrees, hot enough that it emits X-rays, but not dense enough to be easily observable. At the intersections where multiple filaments meet, enormous galaxy clusters form. These are the cities of the cosmic web, containing hundreds or even thousands of galaxies bound together by gravity. The largest galaxy clusters can contain as much mass as 1,000,000 billion suns, most of it in the form of dark matter, with substantial amounts of hot gas filling the space between galaxies. These clusters mark the nodes of the web, the places where matter has concentrated most densely. Between the filaments lie the cosmic voids, vast regions of space that are remarkably empty. A typical void might be 150 million light-years across and contain very few galaxies. These aren't completely empty. They still contain dark matter and some diffuse gas, but their density is only about 10 to 20% of the average density of the universe. Voids expand over time as matter continues to flow out of them toward the filaments and clusters, making them emptier with each passing billion years. The cosmic web reveals itself to astronomers through large-scale galaxy surveys. Telescopes map the positions of millions of galaxies, measuring not just where they appear in the sky, but also how far away they are. This three-dimensional mapping shows the web's structure clearly. Some of the most famous structures include the Sloan Great Wall, a concentration of galaxies stretching across 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. Our own Milky Way galaxy sits within this web, part of what's called the Local Group, a small collection of about 50 galaxies, including the Andromeda Galaxy and various smaller dwarf galaxies. This local group is located on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. Recent mapping has revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 trillion suns. The gas flowing through the cosmic web carries matter from the voids into the filaments, and from the filaments into the galaxy clusters. This flow is not gentle. Gas moving through the filaments can reach speeds of several hundred kilometers per second, and when streams of gas collide at cluster locations, shock waves heat the gas to tremendous temperatures. These shock waves, called accretion shocks, occur at the boundaries of clusters where the web feeds new material into these gravitationally bound systems. Galaxies forming within the filaments have different characteristics than galaxies forming in the voids or clusters. Filament galaxies have better access to the gas supply flowing through the web, which allows them to continue forming stars for longer periods. Cluster galaxies, surrounded by hot gas and interacting frequently with other galaxies, often exhaust their star-forming fuel more quickly. Void galaxies, isolated and with limited gas supply, tend to be smaller and less luminous. The web is not static. It evolves over cosmic time as gravity continues to pull matter along its channels. Computer simulations of the universe's evolution show that the web was less pronounced in the early universe and has become more defined over billions of years. The voids have expanded. The filaments have thinned in some places while becoming more pronounced in others, and the galaxy clusters have grown larger as they consume matter from the surrounding web. Dark energy complicates this picture. This mysterious force which causes the universe's expansion to accelerate works against gravity's tendency to pull matter together. While gravity tries to make the web more concentrated, dark energy pushes space apart. The current era represents a transition. For the first several billion years after the Big Bang, gravity dominated and the web continued to grow more structured. But as dark energy's influence has grown stronger over time, it has begun to limit further structure growth. In the far future, dark energy will win, pulling the filaments apart and eventually isolating each galaxy cluster as an island in an ever-expanding sea of space. Scientists study the cosmic web using multiple techniques. Optical telescopes map the positions of galaxies. Radio telescopes detect the neutral hydrogen gas in and around galaxies. X-ray telescopes observe the hot gas in galaxy clusters and filaments. By combining these different views, astronomers build up a comprehensive picture of where matter exists and how it moves through the web's structure. The web also serves as a cosmic laboratory for studying dark matter. The way galaxies move within filaments and clusters, and the bending of light from distant objects as it passes through the web's mass concentrations, both provide information about the distribution of dark matter. These observations have helped confirm that dark matter exists, and have constrained theories about what dark matter might be, even though its fundamental nature remains one of physics' deepest mysteries. On the very largest scales, the cosmic web shows a surprising degree of uniformity. While the web has complex structure on scales up to a few 100 million light-years, if you average over regions 1 billion light-years or larger, the universe looks remarkably similar in all directions. This homogeneity on the largest scales supports the cosmological principle, the idea that on sufficiently large scales, the universe is essentially the same everywhere, with no preferred locations or directions. The web continues to influence galaxy evolution today. Our own galaxy, the Milky Way, is being pulled through space by the gravitational attraction of the web's structure. We're falling toward the Virgo cluster at about 400 kilometers per second, and at the same time, our entire local supercluster is being pulled toward an even more massive concentration of galaxies in the direction of the constellations Centaurus and Hydra, a region astronomers call the Great Attractor. Understanding the cosmic web means understanding how the universe transformed from a nearly smooth state shortly after the Big Bang into the rich structured cosmos we see today. The web is a fossil record of the universe's history, preserving information about the initial conditions that existed billions of years ago, and documenting the ongoing battle between gravity, trying to pull matter together, and cosmic expansion, trying to spread it apart. Every galaxy in the night sky exists where it does because of this vast structure, this intricate architecture that connects everything in the universe into one enormous, evolving pattern. The different types of habitable planets. When astronomers speak of habitable planets, they often mean worlds similar to Earth, rocky planets with liquid water on their surfaces, orbiting at comfortable distances from sun-like stars. But the discovery of thousands of exoplanets over the past few decades has revealed that planetary systems come in astonishing variety, with planet types that don't exist in our solar system and orbital configurations that defy early expectations. This diversity suggests that habitability, the capacity to support life, might extend far beyond Earth-like worlds to encompass planet types that seem alien at first glance, yet might provide suitable conditions for life to emerge and thrive. Understanding the different types of habitable planets means expanding our definition of habitability beyond the familiar, to consider the full range of worlds where biology might find a foothold. Ocean worlds represent perhaps the most common type of potentially habitable planet. These are planets covered entirely or nearly entirely by deep oceans, with no dry land or only minimal landmass protruding above water. Earth itself is an ocean world to some degree, with about 70% of its surface covered by water, but true ocean worlds might have water covering 95 or even 100% of the surface, with global oceans potentially hundreds of kilometers deep. Such worlds might form beyond the snowline in their stellar systems, where water ice is abundant during formation, then migrate inward to warmer regions where the ice melts, creating global oceans. Life on ocean worlds might never develop terrestrial forms. Everything would evolve in water, from microscopic plankton to potentially large swimming organisms analogous to whales. Without land, there would be no forests, no land animals, no terrestrial plants. But aquatic life could still be extraordinarily diverse and complex. The key question, for ocean worlds is whether photosynthetic life could evolve. Sunlight penetrates only the upper layers of water, so photosynthesis would be restricted to the surface zone. Below a certain depth, life would depend on organic matter sinking from above, or on chemical energy from hydrothermal vents on the ocean floor, much like deep-sea ecosystems on Earth. Extremely deep oceans present another challenge: high-pressure ice. At depths exceeding several hundred kilometers, pressure can become so intense that water freezes despite high temperatures, forming exotic ice structures called Ice 6, Ice 7, and other high-pressure phases that are denser than liquid water. A planet with oceans deep enough to reach these pressures would have a layer of exotic ice separating the liquid ocean from the rocky mantle below. This ice layer would prevent direct contact between water and rock, potentially limiting the availability of minerals and nutrients dissolved from rock that life might need. However, the ice itself might crack due to tidal forces or internal heat, allowing some exchange between the rocky interior and the ocean. Desert planets represent the opposite extreme, worlds where water is scarce, with most of the surface covered by deserts, sand dunes, or bare rock. These planets orbit closer to the inner edge of the habitable zone, where temperatures are higher and water is more likely to evaporate. Any water present might be concentrated in polar ice caps, in subsurface aquifers, or in rare oases where geological features trap moisture. Mars represents a partial example, a cold desert world where water exists mostly as ice or locked in minerals, with liquid water appearing only occasionally in specific locations. Life on desert planets would need extreme water conservation strategies. Organisms might be active only during rare rain events, spending most of their time dormant. They might extract water from humidity in the air or from chemical reactions rather than drinking liquid water. They might have impermeable skins to prevent water loss, and highly efficient kidneys or equivalent organs that recycle water internally. Plant analogues might photosynthesize only at night when temperatures drop and humidity rises, closing all pores during the day to prevent water loss. Despite the harsh conditions, life could potentially thrive in sheltered microenvironments, shaded canyons, caves where humidity condenses, or underground where water from ancient aquifers remains accessible. Eyeball planets emerge around red dwarf stars when planets become tidally locked, always showing the same face to their star, with one hemisphere in permanent daylight and the other in eternal darkness. The day side receives constant intense heating, potentially creating a hot desert. The night side, receiving no sunlight, freezes solid. But at the terminator, the boundary between day and night, a ring of habitable conditions might exist where temperatures remain moderate. This ring might harbour a circular ocean, the eyeball, surrounded by ice on one side and desert on the other, creating a narrow band where life could flourish. Life on eyeball planets would be restricted to this habitable ring, adapted to conditions that never change. No day-night cycle, no seasons, just constant twilight with the star permanently fixed at the horizon. Organisms might spread around the entire circumference of the planet along this habitable band, but they couldn't expand toward either pole. Moving toward the substellar point would lead to lethal heat. Moving toward the antistellar point would lead to frozen darkness. The planet's climate would feature constant winds as air heated on the day side rises and flows toward the cold night side, creating atmospheric circulation patterns completely unlike Earth's weather. Super-Earths, rocky planets more massive than Earth, but less massive than Neptune, might be the most common type of habitable planet in the galaxy, despite having no analogue in our solar system. These worlds, with masses ranging from about 2 to 10 times Earth's mass, would have stronger surface gravity than Earth. An organism on a super-Earth twice Earth's mass might weigh twice what it would on Earth, creating challenges for movement and structural support, but super-Earths have potential advantages for habitability. Their stronger gravity can hold thicker atmospheres more effectively, providing better greenhouse warming and allowing habitable zones to extend farther from their stars. They might have more active plate tectonics due to greater internal heat, helping regulate climate over geological time. Life on super-Earths would likely evolve shorter, stockier body plans to cope with high gravity. Trees might be shorter and thicker. Animals might have more legs or stronger, thicker legs to support their weight. Flight might be more difficult, requiring more powerful wings and muscles. But the thicker atmosphere might actually make flight easier by providing more air resistance, potentially allowing organisms to evolve gliding or flying capabilities using less energy than on Earth, despite the higher gravity. Mini-Neptunes, planets with substantial hydrogen-helium atmospheres surrounding rocky or icy cores, represent a planet type between rocky super-Earths and gas giants. These worlds might not be habitable at their cloud tops where temperatures and pressures are moderate, but atmospheres are thick hydrogen-helium mixtures. However, some mini-Neptunes might have layers within their atmospheres where temperature and pressure allow water vapor to condense into liquid water droplets, creating water clouds and potentially habitable conditions within the atmosphere itself. Aerial life in these water clouds, floating organisms that never touch solid ground because there is no solid ground accessible, might evolve. Such organisms would need to regulate their buoyancy, perhaps using gas-filled bladders similar to fish swim bladders. They might extract nutrients from atmospheric chemistry or from particles suspended in the atmosphere. Reproduction might involve releasing spores or offspring that drift through the atmosphere until they find suitable conditions to grow. The entire biosphere would be three-dimensional and airborne, with no connection to any surface. Hycean worlds, a term combining hydrogen and ocean, represent a recently proposed planet type that might be surprisingly common and habitable. These are large planets with hydrogen-rich atmospheres and liquid water oceans beneath them, potentially including some mini-Neptunes if conditions are right. The thick hydrogen atmospheres would create greenhouse warming that keeps water liquid even at large distances from the star. Life on Hycean worlds would live in the oceans beneath kilometers of hydrogen atmosphere, never exposed to space but potentially able to thrive in the dark, high-pressure water below. The discovery of biosignatures on Hycean worlds might be easier than on Earth-like planets because their larger sizes and extended atmospheres make spectroscopic analysis more favourable. If life produces gases that reach the hydrogen atmosphere, methane, dimethyl sulfide, or other organic compounds, these might be detectable even with current telescope technology. Hycean worlds thus represent prime targets for near-term biosignature searches. Carbon planets might form in regions of protoplanetary disks, where carbon is more abundant relative to oxygen than in our solar system. Instead of being dominated by silicate minerals like Earth, these worlds might have surfaces and interiors rich in graphite, diamond, silicon carbide, and other carbon compounds. The chemistry of such worlds would be radically different from Earth's. Oceans might consist of hydrocarbons, liquid methane, ethane, or more complex carbon compounds, rather than water. Life on carbon planets, if it evolved, would necessarily use chemistry adapted to carbon-rich, oxygen-poor conditions, potentially resembling the hydrocarbon-based biochemistry speculated for Titan. Lava worlds orbit so close to their stars that surface temperatures exceed the melting points of rock. These planets have surfaces of molten lava with atmospheres of vaporized rock, silicate gases that condense into mineral clouds and rain molten droplets. No life as we imagine it could survive on these surfaces, but some scientists speculate about exotic life existing in the upper atmosphere, where temperatures are lower, or about subsurface oceans trapped beneath the molten surface, where water remains liquid despite the hellish conditions above. Ice worlds covered by thick shells of water ice might be habitable not on their surfaces, which are frozen solid, but in subsurface oceans kept liquid by tidal heating from their parent planet's gravity. Jupiter's moon, Europa, and Saturn's moon, Enceladus, represent examples in our own solar system. Such worlds might be common around giant planets throughout the galaxy. The ice shell provides protection from radiation and impact, while the liquid ocean beneath could harbour extensive ecosystems based on chemical energy from hydrothermal vents rather than sunlight. These worlds would have dark biospheres, no photosynthesis, no dependence on their star, just chemosynthetic life, thriving in hidden seas. Rogue planets drifting through interstellar space with no star at all might still be habitable if they're massive enough to retain thick atmospheres that provide greenhouse warming through atmospheric pressure alone. A rogue Earth-mass planet with a very thick hydrogen atmosphere might maintain liquid water on its surface, despite receiving no starlight, heated only by residual internal radioactive decay and gravitational contraction. Life on such a world would exist in perpetual darkness, depending entirely on chemical energy and internal heat, completely independent of any star. A truly alien biosphere that could drift for billions of years through the void between stars. Binary planet systems where two similarly sized worlds orbit their common center of mass, like Pluto and Charon but potentially both habitable, might create unique conditions. Tidal forces between the planets would generate internal heating. The planets would raise tides on each other. If both have atmospheres, atmospheric circulation might be affected by the nearby companion. Life might evolve on both worlds simultaneously, potentially following different evolutionary paths, or life might spread from one to the other via meteorite impacts that eject material-carrying microorganisms between the two worlds. Trojan planets sharing the same orbit around a star, positioned at stable Lagrange, 0.60 degrees ahead of or behind each other, might exist in some systems. These planets would orbit at the same distance from their star, but would see each other as bright points in the sky, visible like particularly bright stars. If both are habitable, civilizations might arise on both, potentially detecting each other's presence long before achieving space travel, since the neighbouring world would be so prominent in their sky. The different types of habitable planets extend far beyond Earth analogues to encompass ocean worlds with global seas, desert planets with scarce water, tidally locked eyeball planets with habitable rings, massive super-Earths with strong gravity, aerial biospheres in thick atmospheres, subsurface oceans beneath ice shells, hydrocarbon-based chemistry on carbon planets, and rogue worlds wandering starless through the galaxy, each type presenting unique challenges and opportunities for life, each potentially harbouring biospheres as rich and complex as Earth's, despite being profoundly different in their physical conditions, demonstrating that the cosmos might contain not just one type of living world, but a vast diversity of habitable environments where chemistry, energy, and time have combined to create the extraordinary phenomenon we call life, scattered across countless worlds in forms we're only beginning to imagine. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival, in boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of barophils, pressure-loving organisms, suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow. But there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons, and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1 million times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles predicted by physics but never observed might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp spacetime. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The powerful magnetic fields of dead stars. When a massive star exhausts its nuclear fuel and explodes as a supernova, the collapsing core is compressed into an object of almost incomprehensible density. A neutron star, containing more mass than the Sun, packed into a sphere only about 20 kilometers across. This violent compression doesn't just create extreme density, it also amplifies the star's magnetic field to strengths that dwarf anything found elsewhere in nature. The magnetic fields of neutron stars are among the strongest in the universe, billions or even trillions of times more powerful than Earth's magnetic field, strong enough to distort atoms, affect the fabric of empty space itself, and dominate the physics of everything near these stellar remnants. To understand how neutron stars develop such powerful magnetic fields, we need to consider what happens during the collapse. Before the supernova, the massive star had a magnetic field similar in strength to the Sun's, a few Gauss at the surface, comparable to a modest laboratory magnet. The star's magnetic field was generated by convection and rotation in its interior, creating currents of electrically conducting plasma that produced magnetism through the same basic dynamo process that generates Earth's magnetic field. When the star's core collapses, it shrinks from a radius of thousands of kilometers down to only about 10 or 12 kilometers, a compression factor of more than 1,000. As the core collapses, magnetic field lines are squeezed together. The strength of a magnetic field is proportional to the density of field lines passing through a given area, so compressing the core concentrates the field lines, amplifying the magnetic field strength enormously. The exact amplification depends on the details of the collapse, but conservation of magnetic flux, a fundamental principle stating that magnetic field lines cannot be created or destroyed, only moved around, requires that the field strength increase roughly in proportion to the decrease in the star's cross-sectional area. Shrinking the radius by a factor of 1,000 increases the magnetic field by about 1,000,000 times. A star with an initial field of 1 Gauss would emerge from collapse as a neutron star with a field of roughly 1,000,000 Gauss, or 1,000 Tesla. This is just the starting point. Most neutron stars have magnetic fields measured in hundreds of millions to trillions of Gauss. Earth's magnetic field, for comparison, measures about half a Gauss at the surface. The strongest continuous magnetic fields produced in laboratories reach around 45 Tesla, or about 500,000 Gauss, requiring enormous electromagnets and tremendous amounts of power. Yet neutron stars casually exceed these laboratory records by factors of millions or billions through nothing more than gravitational compression. Rotation adds another layer of complexity. The collapsing core spins faster as it shrinks, just as a figure skater spins faster when pulling their arms inward. Another consequence of conservation of angular momentum. A star that initially rotated once every few weeks might emerge from collapse rotating several times per second, or even hundreds of times per second. This rapid rotation, combined with the intense magnetic field, creates the phenomenon we observe as pulsars. A pulsar is a rotating neutron star whose magnetic axis is tilted relative to its rotation axis, similar to how Earth's magnetic poles don't align perfectly with the geographic poles. Charged particles near the neutron star's surface are accelerated along the magnetic field lines toward the magnetic poles, where they emit beams of radio waves, X-rays, and sometimes even gamma rays. As the neutron star rotates, these beams sweep through space like lighthouse beams. When one of the beams happens to point toward Earth, we detect a pulse of radiation. The pulses arrive with extraordinary regularity. Some pulsars keep time more accurately than the best atomic clocks over short timescales. The Crab pulsar, formed in the supernova observed in the year 1054, rotates 30 times per second and has a magnetic field estimated at around 1 trillion Gauss. This field is strong enough to do remarkable things. If you could somehow place a human body in such a field, ignoring for the moment all the other ways a neutron star would kill you, the magnetic field would be strong enough to distort your atoms. The field would force electrons into different orbital configurations, changing the chemical properties of matter and making normal biological chemistry impossible. But some neutron stars have magnetic fields even more powerful than typical pulsars. These objects, called magnetars, possess the strongest magnetic fields known in the universe, reaching 10 to the 15th Gauss, or a billion Tesla. These fields are so strong that they affect empty space itself. According to quantum electrodynamics, the quantum field theory describing how light and matter interact, extremely strong magnetic fields can cause the vacuum to behave in strange ways. The vacuum can become birefringent, splitting light into two beams with different polarizations, similar to how certain crystals split light. Virtual particle pairs, electrons and positrons that normally pop briefly into existence and then annihilate, can be affected by the field, altering how light propagates through the vacuum. In magnetar fields, atoms are stretched into elongated shapes, becoming needle-like structures rather than the familiar spherical electron clouds. The magnetic field overwhelms the electric forces that normally determine atomic structure, forcing electrons into highly unusual quantum states. Matter at the surface of a magnetar exists in forms never encountered anywhere else, with properties unlike any material found on Earth or in laboratory experiments. Magnetars reveal their presence through sudden outbursts of X-rays and gamma rays. The magnetic field stores enormous amounts of energy. In the strongest magnetars, the magnetic energy exceeds the binding energy holding the neutron star together, creating immense internal stresses. The neutron star's crust, composed of crystallized nuclear matter, occasionally cracks under these stresses in events called starquakes. When the crust suddenly shifts, the magnetic field lines snap and reconnect violently, releasing tremendous bursts of energy in seconds or less. The most powerful magnetar flare ever observed occurred in December 2004 from a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth. In 1/10 of a second, this flare released more energy than the Sun emits in 150,000 years. The radiation from this event saturated detectors on satellites throughout the solar system and measurably affected Earth's ionosphere, despite the enormous distance. If this magnetar had been located only 10 light-years from Earth instead of 50,000 light-years away, the flare would have caused a mass extinction, stripping away the ozone layer and exposing the surface to lethal radiation. The origin of magnetar fields remains somewhat mysterious. The simple compression of the collapsing star's field cannot account for fields this strong. Magnetar fields are hundreds to thousands of times stronger than what compression alone would produce. Several theories attempt to explain the enhancement. One possibility involves a dynamo mechanism operating in the first few seconds after the neutron star forms, when the core is still extremely hot and turbulent. Convection in the proto-neutron star, combined with rapid rotation, might amplify the magnetic field through a dynamo process, similar to how Earth generates its field, but operating under extreme conditions for a brief time. Another possibility involves the formation mechanism itself. If the collapsing core rotates very rapidly, near the maximum possible rate, differential rotation between the inner and outer parts of the core might stretch and amplify magnetic field lines, winding them up like a spring and creating the immensely powerful fields observed in magnetars. This would suggest that magnetars are born from progenitor stars that were rotating particularly rapidly before collapse, or from binary star systems where mass transfer spun up the star before the supernova. The magnetic fields of neutron stars gradually decay over time. The field energy is dissipated through various processes, including emission of electromagnetic radiation and heating of the neutron star's interior. Typical pulsars with fields around 1 trillion Gauss might maintain those field strengths for millions of years. Magnetar fields, being much stronger, decay more quickly, possibly over tens of thousands of years. As magnetars age and their fields weaken, they might become ordinary pulsars indistinguishable from neutron stars that never had magnetar strength fields. This decay helps explain why magnetars are relatively rare. Astronomers have identified only about 30 confirmed magnetars in our galaxy, compared to thousands of ordinary pulsars. If magnetar fields decay on timescales of 10,000 to 100,000 years, and they form perhaps once every few hundred years in our galaxy, then at any given time, only a few dozen active magnetars would exist, which matches observations well. The magnetic fields don't just affect the neutron star itself, they extend outward into space, creating a magnetosphere. Charged particles near the neutron star cannot cross magnetic field lines easily, so they become trapped, spiraling along the field lines. The field forces these particles to co-rotate with the neutron star out to a distance called the light cylinder, where the co-rotation velocity would equal the speed of light if the field could enforce it. Beyond the light cylinder, particles can escape along the field lines, carrying energy and angular momentum away from the neutron star. This energy loss causes pulsars to gradually slow down. The Crab pulsar's rotation period increases by about 38 nanoseconds per day, as it loses rotational energy to the magnetic field and the wind of particles it drives. The rate of slowdown reveals how much energy the pulsar is radiating. Young pulsars with strong magnetic fields slow down quickly. Old pulsars with weaker fields slow down more gradually. By measuring both the rotation period and the slowdown rate, astronomers can estimate a pulsar's age and magnetic field strength. Some of the fastest spinning pulsars, called millisecond pulsars because they rotate hundreds of times per second, have much weaker magnetic fields than typical pulsars. These objects were spun up to high speeds by accreting matter from a companion star in a binary system. The infalling matter transferred angular momentum to the neutron star, spinning it up, while simultaneously burying the magnetic field under a layer of accreted material, weakening the external field. These recycled pulsars have been rejuvenated by mass transfer, given a second life as rapidly spinning objects with relatively weak fields. The study of neutron star magnetic fields connects to fundamental physics in several ways. These fields exist at strengths where quantum electrodynamics predicts effects that cannot be tested in any laboratory. Observations of magnetars and the radiation they emit provide the only way to study matter and vacuum behavior in such extreme magnetic environments. The fields also affect how nuclear matter behaves at the neutron star surface and in the crust, influencing the equation of state, the relationship between pressure and density of matter at nuclear densities and beyond. Binary systems containing two neutron stars allow even more exotic magnetic interactions. When two magnetized neutron stars orbit close together, their magnetic fields can interact, possibly reconnecting and releasing energy. As the neutron stars spiral together, driven by gravitational wave emission, the magnetic fields might play a role in the final moments before merger, potentially affecting the gravitational wave signal and the electromagnetic radiation emitted during the kilonova that follows. The powerful magnetic fields of dead stars represent nature operating at extremes impossible to recreate artificially, fields where quantum effects modify the behavior of empty space, where atoms are distorted beyond recognition, and where enough energy is stored to power the sun for millennia, all concentrated in objects small enough to fit inside a city, yet massive enough to contain more matter than an entire star. Fields that define the physics of these remarkable objects and make them among the most extreme environments existing anywhere in the cosmos. The thick atmospheres of Jupiter and Saturn. Jupiter and Saturn are fundamentally different from the rocky planets of the inner solar system. They have no solid surface to stand on, no ground beneath the sky. Instead, these gas giants are essentially enormous atmospheres all the way down, layers upon layers of gas that gradually transition from thin upper hazes to dense, crushing depths, where pressure transforms hydrogen into states of matter that don't exist naturally anywhere on Earth. Understanding these thick atmospheres means understanding worlds where the atmosphere isn't just a thin shell surrounding a planet, it is the planet. The atmospheres of Jupiter and Saturn are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules, with trace amounts of methane, ammonia, water vapor, and other compounds making up less than 1%. Saturn has a similar composition, though with slightly less helium, about 96% hydrogen and 3% helium, with the missing helium thought to have settled deeper into the planet's interior over billions of years. This composition mirrors the composition of the Sun and the primordial solar nebula from which the planets formed, marking these giants as worlds that captured and retained their original atmospheres from the planet-forming disk. The visible clouds we see when we look at Jupiter and Saturn exist in the uppermost layers of these atmospheres, in a region where temperatures and pressures allow various compounds to condense into droplets and crystals. On Jupiter, the highest cloud layer consists of ammonia ice crystals forming at temperatures around -150 degrees Celsius, where ammonia gas freezes into white ice. These ammonia clouds give Jupiter's zones, the bright bands that circle the planet, their brilliant white appearance. Below this ammonia layer, at slightly higher temperatures and pressures, ammonium hydrosulfide forms another cloud deck, creating brown and tan colours. Deeper still, water ice and liquid water droplets form clouds, though these are rarely visible from above, hidden beneath the overlying layers. Saturn's cloud structure is similar but more subdued. The planet appears more uniformly golden tan because a high-altitude haze of unknown composition partially obscures the underlying cloud layers. This haze may consist of complex organic molecules called tholins, created when ultraviolet light from the sun breaks apart methane molecules in the upper atmosphere, allowing the fragments to recombine into larger, more complex hydrocarbons. These organic hazes absorb blue light and scatter red and yellow light, giving Saturn its characteristic buttery colour. The temperatures in these atmospheres change dramatically with depth. At the cloud tops, where pressure is similar to Earth's atmospheric pressure at sea level, temperatures on Jupiter hover around -145 degrees Celsius. On Saturn, they're even colder, around -180 degrees Celsius, because Saturn is nearly twice as far from the Sun and receives less solar heating. But as you descend into these atmospheres, temperatures rise rapidly. The increase comes partly from the Sun's heat that has been absorbed and transported downward, but more significantly from the planet's internal heat. Both Jupiter and Saturn emit more energy than they receive from the Sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight, while Saturn radiates about 1.8 times as much. This extra energy comes from the planet's interiors. Jupiter is still slowly contracting under its own gravity, a process that converts gravitational potential energy into heat through a mechanism called Kelvin-Helmholtz contraction, named after the physicists Lord Kelvin and Hermann von Helmholtz, who described this process in the 19th century. Saturn has an additional heat source. Helium is slowly separating from hydrogen in its interior and sinking toward the center, releasing gravitational energy as it falls. Much like rain falling through Earth's atmosphere releases energy. This internal heat drives powerful convection in the atmospheres. Warm gas rises from the depths, cools as it rises and expands, then sinks back down to be heated again. This convection creates enormous circulation cells that organize the atmospheres into the distinctive banded patterns visible on both planets. Rising gas forms the bright zones, where fresh ammonia ice crystals condense and create white clouds. Sinking gas forms the darker belts, where descending motion prevents cloud formation and allows us to see deeper into the atmosphere, where darker compounds and higher temperatures exist. The winds on Jupiter and Saturn are among the strongest in the solar system. Jupiter's equatorial region rotates faster than the rest of the planet, with winds reaching speeds of about 360 kilometers per hour, roughly 225 miles per hour. Saturn's equatorial winds are even more extreme, racing along at up to 1,800 kilometers per hour, over 1,100 miles per hour, making them the fastest planetary winds in the solar system. These winds are organized into jet streams, narrow bands of fast-flowing gas that separate the zones and belts. The jet streams are remarkably stable, maintaining their positions and speeds for decades or longer. The Great Red Spot on Jupiter is perhaps the most famous atmospheric feature in the solar system. This enormous storm, large enough to swallow 2 or 3 Earths, has been observed continuously since at least 1830, and possibly as far back as the 1660s, when early telescope observers noted a large spot on Jupiter. The storm is an anticyclone, rotating counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching 400 kilometers per hour. The storm's longevity remains somewhat mysterious. On Earth, hurricanes dissipate within days or weeks when they move over land or cooler water, but the Great Red Spot has persisted for centuries. Its stability likely comes from the fact that Jupiter has no solid surface to create friction and slow the winds, and the storm may draw energy from the smaller storms it absorbs, and from the temperature difference between the warm interior and cold upper atmosphere. Saturn hosts similar, but generally smaller and shorter-lived storms. Approximately once per Saturnian year, about every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, growing to encircle the entire planet before eventually dissipating. These great white spots, as they're called, were observed in 1876, 1903, 1933, 1960, 1990, and 2010, following a remarkably regular pattern tied to Saturn's seasons. The storms appear to originate when seasonal heating destabilizes the atmosphere, allowing deep, moist convection to punch through the stable layers above and create violent thunderstorms. Lightning occurs on both Jupiter and Saturn, detected by the Voyager, Galileo, and Cassini spacecraft through radio emissions and, in some cases, visible flashes. The lightning on these worlds is similar to terrestrial lightning, electrical discharges between regions of different charge within clouds, but can be far more powerful than Earth's lightning. Individual lightning bolts on Saturn have been measured at up to 1 million times more powerful than typical lightning on Earth. These storms occur in the water cloud layer, where the same process that creates thunderstorms on Earth, rising moist air forming clouds and separating electrical charges, operates on these giant planets. As you descend deeper into these atmospheres, the pressure increases relentlessly. At depths of a few hundred kilometers below the cloud tops, pressures reach thousands of times Earth's atmospheric pressure, and temperatures climb to hundreds of degrees Celsius. The atmosphere becomes denser and denser, transitioning gradually from gas to liquid, though there's no sharp boundary, no ocean surface where you suddenly plunge from air into water. Instead, the hydrogen and helium gradually become so compressed that they take on liquid properties, while still being hot enough that calling them liquid doesn't quite capture their state. They exist in a supercritical fluid state, where the distinction between gas and liquid breaks down. Descend even deeper, to depths of 10,000 to 20,000 kilometers, and pressures reach millions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen transforms into metallic hydrogen, a state of matter where the atoms are squeezed so tightly that their electrons are freed from individual atoms and flow through the material like electrons in a metal. This metallic hydrogen is thought to make up the bulk of Jupiter's mass and a significant portion of Saturn's. It's an excellent electrical conductor, and the flow of metallic hydrogen in these regions, driven by the planet's rotation and internal convection, generates the powerful magnetic fields that both planets possess. The transition from molecular hydrogen to metallic hydrogen isn't abrupt. There's a gradual change over a range of depths where hydrogen takes on increasingly metallic properties. Scientists study this transition using laboratory experiments that compress hydrogen to extreme pressures and sophisticated computer simulations that model how atoms behave under conditions impossible to fully recreate on Earth. Understanding metallic hydrogen is crucial for understanding the interiors of Jupiter and Saturn, yet its properties remain uncertain because the pressures required, several million times atmospheric pressure, can only be achieved briefly in laboratory settings. At the very centers of Jupiter and Saturn may lie rocky cores, though whether these cores exist and how large they might be remains debated. Jupiter might have a core of rock and ice, containing 10 to 20 Earth masses, or it might have no distinct core at all, just a gradual increase in the concentration of heavy elements toward the center. Saturn might have a similar core, though perhaps smaller relative to the planet's total mass. NASA's Juno mission to Jupiter and the Cassini mission's final orbits, diving between Saturn and its rings, have provided gravity measurements precise enough to constrain the planet's interior structures, revealing that both planets have somewhat diffuse cores rather than sharp boundaries between core and envelope. The scale of these atmospheres is almost incomprehensible. On Earth, the atmosphere extends perhaps 100 kilometers before space begins. On Jupiter and Saturn, the atmosphere extends downward for thousands upon thousands of kilometers, transitioning through states from thin gas to dense supercritical fluid to liquid metallic hydrogen. If you could somehow survive the crushing pressures and searing temperatures and descend through Jupiter's atmosphere, it would take days or weeks of continuous falling to reach the planet's center, passing through layer after layer of hydrogen in different states, all of it technically atmosphere, because there's no solid surface to mark where the atmosphere ends. The study of Jupiter's and Saturn's atmospheres extends beyond academic interest. Understanding how these atmospheres work, how convection organizes into bands, how storms form and persist, how energy is transported from the interior to space, helps scientists understand atmospheric dynamics more broadly. The principles governing Jupiter's atmosphere apply, with appropriate modifications, to Saturn's atmosphere, to the atmospheres of Uranus and Neptune, and even to the atmospheres of giant exoplanets orbiting other stars. Some exoplanets, called hot Jupiters, orbit extremely close to their stars and have atmospheres heated to thousands of degrees, creating extreme versions of the processes we observe on Jupiter and Saturn. These thick atmospheres also serve as laboratories for studying hydrogen under extreme conditions. Most of the normal matter in the universe is hydrogen, and understanding how it behaves under high pressure is crucial for understanding not just giant planets, but also brown dwarfs, objects intermediate in mass between planets and stars, and the interiors of low-mass stars. The hydrogen in Jupiter and Saturn exists across a range of pressures and temperatures that spans from Earth-like conditions in the upper atmosphere to conditions approaching those in stellar interiors in the metallic hydrogen regions, providing natural experiments that inform our understanding of matter itself across a vast range of conditions. What alien civilizations might actually look like? When most people imagine alien civilizations, they picture humanoid beings with large heads, sleek bodies, and advanced technology that allows them to cross the vast distances between stars. Science fiction has given us countless variations: green-skinned Martians, insectoid hive minds, crystalline energy beings, peaceful explorers, and hostile invaders alike. But what would alien civilizations actually look like if we base our expectations on biology, physics, chemistry, and evolutionary principles rather than imagination alone? The answer reveals possibilities both familiar and utterly strange, shaped by the same fundamental laws that govern life on Earth, but expressed through the infinite variations that different worlds and evolutionary histories would create. The foundation of any alien civilization begins with evolution. On Earth, every organism exists because its ancestors survived and reproduced more successfully than competitors. Natural selection shaped everything from bacterial flagella to human brains, optimizing organisms for their specific environments and challenges. The same process would operate on any world where life exists. Alien organisms would be shaped by their planet's gravity, atmosphere, temperature, available nutrients, predators, and countless other factors operating over millions or billions of years. Evolution is relentless, creative, and opportunistic, finding solutions to survival challenges through whatever mechanisms work. Gravity would profoundly influence alien body structures. On a high-gravity planet, perhaps 1.5 times Earth's gravity, organisms would need stronger skeletal structures to support their weight. Animals might evolve shorter, stockier bodies with thicker bones and more powerful muscles. Tall, slender forms would be disadvantageous because they would require too much structural support and energy to maintain. Intelligent beings on such a world might stand only 3 or 4 feet tall despite being as massive as humans, with powerful legs and low centers of gravity to move efficiently under the stronger gravitational pull. On a low-gravity planet, the opposite constraints would apply. With less gravitational force to overcome, organisms could grow taller and more delicate. Bones could be lighter and more slender. Flying might be easier, allowing evolution to produce larger flying organisms than Earth's giant pterosaurs. Intelligent beings might stand 8 or 10 feet tall with elongated limbs, moving with a grace that would seem almost balletic to Earth-based observers. Their skeletal structure might resemble bird bones, hollow and reinforced with internal struts rather than solid like mammalian bones. The atmospheric composition would shape how aliens breathe and what biochemistry they use. On Earth, most complex life uses oxygen for metabolism because burning fuel with oxygen releases large amounts of energy efficiently. But oxygen was not always abundant. Early Earth had an atmosphere dominated by nitrogen, carbon dioxide, methane, and other gases. The oxygen we breathe today came from photosynthetic bacteria that gradually transformed the atmosphere over billions of years in what's called the Great Oxidation Event. An alien planet might never undergo such a transformation, leaving its atmosphere oxygen poor. Life there might use different metabolic pathways, perhaps based on sulfur compounds, hydrogen, or methane. The type of star a planet orbits would influence alien vision and perhaps their entire sensory experience of reality. Our sun emits most strongly in visible light wavelengths, the colours we can see, and Earth's organisms evolved eyes sensitive to these wavelengths because that's where the most light was available. But a planet orbiting a red dwarf star would receive most of its light in infrared wavelengths. Organisms evolving there might develop eyes sensitive to infrared rather than visible light. To them, what we call visible light might be invisible ultraviolet, and their daylight would be our infrared. An alien from such a world would perceive colours and see objects in ways completely foreign to human experience. Conversely, a planet orbiting a hotter, bluer star would receive more ultraviolet light. Evolution might produce eyes sensitive to ultraviolet wavelengths, allowing these aliens to see patterns and colours invisible to humans. Many Earth organisms, including bees and some birds, can already see into the ultraviolet range, perceiving patterns on flowers and plumage that humans cannot detect without special cameras. An alien species with full ultraviolet vision would experience a visual world enriched with information and beauty we cannot access. Communication methods would evolve based on environmental constraints and available sensory channels. On Earth, humans primarily communicate through sound, speaking and hearing, supplemented by visual cues like facial expressions and gestures. But sound travels poorly, in thin atmospheres, and not at all in vacuum. An alien species on a world with a thin atmosphere might rely more heavily on visual communication, colour changes, bioluminescent patterns, or elaborate gestural languages. Octopuses on Earth already use colour-changing skin cells, called chromatophores, to communicate, creating flowing patterns across their bodies. An intelligent species with similar abilities might communicate through rapidly shifting colour displays, conveying complex ideas through patterns that flow across their skin in what would appear to us as living art. Some aliens might communicate through vibrations transmitted through the ground or through their planet's oceans. Whales and elephants on Earth use low-frequency sounds that travel great distances. Elephant calls can travel several miles through the ground. An intelligent species might evolve specialized organs for creating and detecting vibrations, communicating through seismic signals that travel through rock or sediment. Their language would be invisible and inaudible to humans without special equipment to detect the vibrations. Chemical communication, already used extensively by Earth's insects through pheromones, might become the primary communication method for some species. Aliens might communicate through releasing complex mixtures of chemicals that other members of their species detect through sensitive chemoreceptors. Their language would consist of scents and tastes with grammar and syntax encoded in the ratios and combinations of different molecules. To humans, their most profound poetry and scientific papers would be nothing more than smells. Body structure would reflect evolutionary history and environmental pressures. The bilateral symmetry seen in most Earth animals, a left side mirroring a right side, emerged early in evolution and became locked in. But aliens might evolve radial symmetry, like starfish, with body parts arranged around a central axis. An intelligent being with radial symmetry might have arms, eyes, and sensory organs distributed evenly around their body, giving them a 360-degree field of awareness with no natural front or back. Their psychology and culture might be profoundly affected by experiencing the world without a preferred direction of travel or attention. The number of limbs is not fixed by any physical law. Earth's vertebrates settled on 4 limbs relatively early in evolutionary history, but arthropods, insects, spiders, crustaceans have 6, 8, or even dozens of legs. An alien species might evolve with 3 limbs arranged in a triangle, giving them stable tripod support at all times. They might have 6 limbs, 4 for walking and 2 manipulator arms. Or they might have dozens of tentacles like an octopus, each capable of independent complex movement and manipulation. Their tool use and technology would develop along entirely different lines than human technology, shaped by their different manipulative abilities. Intelligence itself might manifest in forms unlike human intelligence. Human intelligence is highly centralized. Most of our cognitive processing occurs in our brain, a single organ in our head. But octopuses, among Earth's most intelligent invertebrates, have a distributed nervous system with neurons throughout their arms that can make independent decisions. An alien species might have multiple brain centers distributed throughout their body, or they might have a collective intelligence where individual organisms are relatively simple, but groups display emergent intelligence through their interactions, similar to how ant colonies solve complex problems that individual ants cannot. Social structure would influence civilization development. Humans are intensely social primates who naturally form groups, cooperate, compete, and create complex hierarchies. An intelligent species that evolved from solitary predators might have very different social instincts, perhaps coming together only to mate and raise young, then separating again. Their civilization would be built by individuals who value isolation and independence over community and cooperation. Or aliens might be eusocial, like bees or ants, with specialized castes, workers, soldiers, reproducers, genetically programmed for different roles. Their civilization might function as a superorganism where individual identity barely exists. Lifespan would profoundly affect culture and technology development. If an alien species naturally lives for thousands of years, they might approach problems with a patience humans cannot fathom, willing to spend centuries on single projects. Their sense of urgency and change would operate on timescales that would frustrate any human trying to interact with them. Conversely, a species with lifespans of only a few years might compress their entire cultural and technological development into periods that humans would find incomprehensibly rapid. Environmental factors would shape not just biology, but psychology and culture. A species that evolved in oceans might think about space and boundaries very differently than land-dwelling humans. Without solid ground beneath them, without permanent structures that last for generations, their concepts of property, territory, and permanence might be fluid in ways humans struggle to understand. A species that evolved in dense forests with limited sightlines might have very different concepts of distance and perspective than humans who evolved in open savannas, where seeing for miles was possible and valuable. Technology would develop based on available resources and environmental challenges. A civilization on a water world with no dry land would never discover fire, fundamentally altering their technological development pathway. Without fire, they couldn't easily work metals, make pottery, or develop steam power. Their technology might focus on biological engineering, breeding organisms to serve specific functions, or on working with materials that don't require heat processing. They might develop advanced understanding of hydrodynamics, pressure, and acoustic phenomena, while lacking technologies that humans developed early. A civilization on a planet with extreme temperature swings might prioritize insulation and environmental control. A species on a tidally locked planet with one side in permanent daylight and the other in eternal darkness might build their civilization in the twilight zone between extremes. Or they might develop 2 separate cultures adapted to the radically different environments. Their technology would need to handle these extremes, perhaps leading to advanced materials science long before other fields developed. Reproduction methods would influence family structures and social organization. If aliens reproduce through spawning like fish, releasing eggs and sperm into water where fertilization occurs externally, they might have no concept of nuclear family or parental bonds. Eggs might be raised communally or even left to develop independently. If reproduction requires 3 or more sexes simultaneously, their social structures and mating rituals would be incomprehensibly complex to humans. If they reproduce through budding or fission, creating genetic copies of themselves, their concepts of individuality and identity might be fundamentally different from species that reproduce sexually and value genetic diversity. Sensory experiences beyond human comprehension might exist. Some Earth organisms detect magnetic fields, electric fields, pressure changes, or polarized light, senses humans lack entirely. An alien species might perceive reality through senses we don't possess and cannot easily imagine. They might see the world through echolocation like bats, building a sonic map of their environment. They might sense electrical fields like sharks detecting the bioelectric signatures of other organisms. They might perceive time differently, with reaction times much faster or slower than humans, making their subjective experience of duration incompatible with ours. The Fermi paradox asks why, if alien civilizations are likely to exist, we haven't detected them yet. One possible answer is that we're looking for the wrong things. We search for radio signals because that's how we communicate, and we look for visible structures, like cities, because that's how we build. But an alien civilization might never develop radio technology, using entirely different communication methods. They might build in ways that leave no visible trace from space. They might exist on entirely different timescales, civilizations that rise and fall in centuries, while humans are still learning to farm, or civilizations that operate so slowly that their entire recorded history spans less time than a human lifetime. If contact ever occurs between human and alien civilizations, the challenges would be immense. Even if both species are trying to communicate, fundamental differences in sensory experience, cognition, timescales, and conceptual frameworks might make mutual understanding nearly impossible. Imagine trying to explain color to someone born blind, or music to someone born deaf, or love to a species that doesn't experience emotions. Now multiply those challenges by every aspect of existence: time, space, causation, identity, purpose. Communication might require generations of effort and specialized translation technologies we haven't yet imagined. What alien civilizations might actually look like encompasses possibilities ranging from vaguely familiar, carbon-based organisms breathing oxygen on Earth-like worlds, shaped by convergent evolution into forms somewhat similar to Earth's creatures, to utterly incomprehensible beings whose very existence challenges our definitions of life, intelligence, and civilization. They might be silicon-based entities living in molten rock at temperatures that would vaporize Earth's organisms. They might be electromagnetic patterns in planetary magnetic fields, or chemical reaction networks in liquid methane seas, or quantum coherence patterns in neutron star crusts. The universe is vast and ancient, and if intelligence has emerged elsewhere, it has had billions of years and countless different environments in which to develop into forms limited only by physics, chemistry, and the creative power of evolution, operating across deep time on worlds we've never seen. The zone where life could exist. Life as we know it requires certain conditions to exist. Too hot, and water boils away. Too cold, and water freezes solid. Without liquid water, life as we understand it cannot survive, at least not the kind of carbon-based, water-dependent life that evolved on Earth. This simple requirement creates a critical region around every star called the habitable zone, sometimes nicknamed the Goldilocks zone, because conditions there are neither too hot nor too cold, but just right for liquid water to exist on a planet's surface. Understanding this zone and what makes it special reveals both the requirements for life and the astonishing variety of places in the universe where life might possibly emerge. The habitable zone is not a single precise distance from a star, but rather a range of distances, a band extending outward from the star where temperatures allow water to remain liquid. For our Sun, this zone extends roughly from about 90 million kilometers to about 150 million kilometers from the Sun. Earth, orbiting at about 150 million kilometers, sits comfortably within this zone, though closer to the inner edge than the middle. Venus, at about 108 million kilometers, orbits just inside the inner edge, where temperatures are too high. Its surface temperature exceeds 450 degrees Celsius, hot enough to melt lead, far too hot for liquid water. Mars, at about 230 million kilometers, orbits near or just beyond the outer edge, where temperatures are generally too cold. Though liquid water might occasionally exist in certain locations under special conditions. The boundaries of the habitable zone depend entirely on the star's properties. Hotter, brighter stars have habitable zones located farther out because their intense radiation heats planets to higher temperatures. Cooler, dimmer stars have habitable zones located much closer in. A red dwarf star, the most common type of star in the galaxy, might be only 1/10 as luminous as the Sun, meaning its habitable zone would be about 1/3 the distance from the star. A planet orbiting in the habitable zone of a red dwarf might orbit only 10 million kilometers from its star, closer than Mercury orbits our Sun, yet still maintain temperatures suitable for liquid water because the star is so much dimmer. The habitable zone also depends on the planet's atmosphere. A thick atmosphere with greenhouse gases can trap heat and keep a planet warm even if it orbits farther from its star than the outer edge of the simple, habitable zone. Venus demonstrates the opposite effect. Its extremely thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat so efficiently that surface temperatures soar far beyond what you would expect from Venus's distance from the Sun alone. Without this greenhouse effect, Venus might be cool enough for liquid water. With it, the planet is an inferno. Mars provides another instructive example. Mars orbits near the outer edge of the Sun's habitable zone, and its thin atmosphere, less than 1% the pressure of Earth's atmosphere, cannot retain much heat. Surface temperatures average around -60 degrees Celsius, far too cold for liquid water most of the time. But billions of years ago, Mars had a thicker atmosphere and likely had liquid water flowing on its surface, creating the river valleys and lake beds that spacecraft have photographed. Mars lost most of its atmosphere over time, probably because its weak magnetic field couldn't protect the atmosphere from being stripped away by the solar wind. The planet moved out of effective habitability not by changing its orbit, but by losing the atmosphere that kept it warm. Earth maintains liquid water on its surface through a fortunate combination of factors. Our distance from the Sun provides a baseline amount of heating. Our atmosphere, with modest amounts of carbon dioxide and water vapor, acting as greenhouse gases, traps enough heat to raise the surface temperature by about 33 degrees Celsius, above what it would be without an atmosphere. Our magnetic field, generated by the liquid iron core's motion, shields the atmosphere from the solar wind, preventing the atmospheric loss that doomed Mars. Our planet's size gives it enough gravity to hold onto its atmosphere over billions of years. But the habitable zone is more complex than just distance from a star and atmospheric composition. Other factors influence whether life could actually emerge and survive. Planetary mass matters. A planet too small cannot retain an atmosphere because its weak gravity allows atmospheric gases to escape to space. A planet too large might have such a thick atmosphere that surface pressures become extreme, or might retain so much hydrogen and helium from its formation that it becomes more like a miniature gas giant than a terrestrial world. The planet's rotation rate influences habitability as well. A planet that rotates very slowly or is tidally locked to its star, showing the same face always toward the star as the Moon does to Earth, would have extreme temperature differences between the permanent day side and permanent night side. The day side might be too hot for liquid water, while the night side freezes. Venus rotates extremely slowly, taking more than 200 Earth days to complete one rotation, though its thick atmosphere distributes heat efficiently enough that temperatures are fairly uniform across the planet, despite this slow rotation. Stellar variability affects the habitable zone's stability over time. The Sun's luminosity has increased by about 30% over its lifetime. Early in Earth's history, when the Sun was dimmer, Earth received less heat. Yet geological evidence shows that liquid water existed on Earth's surface going back nearly 4 billion years, despite the fainter Sun. This is called the faint young Sun paradox. The solution probably involves a thicker atmosphere with more greenhouse gases in Earth's past, compensating for the dimmer Sun and keeping temperatures warm enough for liquid water. As stars age, their habitable zones move outward. The Sun will continue brightening over the next billion years or so. Eventually, perhaps in 1 billion to 1.5 billion years, the Sun will become bright enough that even with our current atmosphere, Earth's surface will become too hot for liquid water. The oceans will evaporate, water vapor will accumulate in the atmosphere, and the increased greenhouse effect will push temperatures even higher in a runaway process. Earth will exit the habitable zone, not because Earth moves, but because the habitable zone moves outward as the Sun brightens. Subsurface habitability expands the possibilities beyond the traditional habitable zone. Moons orbiting gas giant planets can have liquid water beneath their icy surfaces, even if they orbit well outside the star's habitable zone. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have subsurface oceans kept liquid by tidal heating, the gravitational squeezing from their parent planets that generates internal heat. These moons demonstrate that life might not require surface liquid water or even a planet within the traditional habitable zone. The requirements might simply be liquid water somewhere, an energy source, and the right chemical ingredients. Tidal heating expands the possible locations for life significantly. A planet or moon doesn't need to orbit at a specific distance from its star if internal heat from tidal forces can keep subsurface water liquid. This might be particularly important for moons orbiting planets in the habitable zones of red dwarf stars, where tidal locking to the star might make surface habitability challenging, but subsurface oceans remain possible. The chemical composition of the planet matters as much as its location. Life requires more than just water. It needs raw materials. Carbon, nitrogen, phosphorus, sulfur, and trace amounts of many other elements are essential for the biochemistry we know. Planets that form too close to their star might lack volatile elements like carbon and nitrogen that are essential for life. Planets that form too far out and then migrate inward might have compositions dominated by ices, rather than having the right balance of rock, metal, water, and organics. Stellar type influences habitability in ways beyond just temperature. Red dwarf stars, while having habitable zones close in, pose challenges for life. These stars frequently produce powerful flares, sudden bursts of radiation, and charged particles that could strip away planetary atmospheres and damage biological molecules. A planet in the habitable zone of a red dwarf would need a strong magnetic field to protect against this radiation. Additionally, red dwarfs are so dim that their habitable zone planets likely become tidally locked, always showing the same face to the star, which creates the extreme temperature contrast problem. More massive stars, while having habitable zones farther out, present a different problem. They burn through their fuel quickly and don't live long enough for complex life to evolve. A star twice the Sun's mass might only live a few billion years before exhausting its hydrogen fuel and evolving into a red giant. On Earth, simple life emerged fairly quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. More massive stars might not remain stable long enough for complex life to evolve on their planets. Binary star systems where two stars orbit each other create more complicated habitable zones. If the stars orbit close together, planets might orbit far enough from both stars that the pair acts like a single brighter star, creating a habitable zone at a large distance. If the stars are widely separated, planets might orbit just one star in a habitable zone, determined primarily by that star's properties. But intermediate cases, where the stars are separated by distances comparable to their habitable zones, create complex and potentially unstable conditions for planets. The galactic habitable zone adds another layer of consideration. Different regions of the galaxy have different properties relevant to life. Near the galactic center, stars are packed more densely, and supernova explosions occur more frequently, potentially sterilizing planets with intense radiation. Far in the outer reaches of the galaxy, stars might be too poor in heavy elements to form rocky planets with the chemical complexity needed for life. The region where our Sun orbits, about halfway out in the galactic disk, might represent a galactic habitable zone where conditions are most favorable for life to emerge and survive long term. Exoplanet discoveries have found thousands of planets, many within their stars' habitable zones. Proxima Centauri b, orbiting the nearest star to our Sun, sits within its star's habitable zone, though whether it actually has liquid water and a protective atmosphere remains unknown. Kepler and other missions have found dozens of roughly Earth-sized planets in habitable zones, though determining which of these might actually host life requires detailed atmospheric studies that current telescopes can barely begin to perform. The concept of habitability continues evolving as we learn more about the diversity of planetary environments. Life might exist in forms very different from Earth's biology, adapted to environments we would consider extreme. Subsurface oceans beneath ice shells, atmospheres of exotic chemistry on planets very different from Earth, even clouds in the atmospheres of gas giants. All these represent potential habitats that expand the zone where life might exist far beyond the simple band of distance where liquid water exists on a planet's surface. The habitable zone represents our best current understanding of where to look for life, based on the one example we have: Earth. It's a starting point, a place to begin the search, knowing that life's possibilities might extend far beyond this simple definition. The zone where life could exist might be much larger than we imagine, encompassing not just planets at the right distance from their stars, but moons with tidal heating, planets with exotic chemistries, and environments we haven't yet conceived, each one a potential home for biology waiting to be discovered.